cosmology, there's been a total revolution. And so we have a huge amount of information that we now know. And if you want to learn about cosmology, you just got to learn this information, because that's what cosmology is all about. It's a science. So what I'm going to do in this lecture is present what I call an historical introduction to lambda CDM cosmology. Lambda CDM is the standard modern model, modern theory. And the next lecture today is an introduction to general relativity. And I'm not quite sure what Lenny Susskind is going to talk about, but I suspect it's going to be applying general relativity and quantum mechanics together to discuss black holes. And so you've seen the schedule for this week. Each day, I think we're sticking to a schedule of 3 lectures, and we'll try to keep the lectures crisp and to the point, because there is a lot of information. So, can everybody read this okay? So, what I'm going to do is talk about, especially the discovery that the universe is almost entirely invisible. That practically all the mass is some invisible stuff called dark matter. Almost all the mass of ordinary matter, atomic stuff, is also invisible. And the vast majority of the energy density of the universe is actually some yet further mysterious component called dark energy. By about the year 2000, this was essentially accepted by almost all astronomers as the basic story. But since then, especially starting in 2003 with the first release of the data from the Wilkinson Microwave Anisotropy Probe, NASA's Cosmic Background Explorer satellite, and then with increasing data from large-scale structure studies the distribution of galaxies nearby and far away, and then finally, just March 21st of this year, the release of the Planck data, which is much more precise than the WMAP data. So the confirmation of the basic predictions of lambda CDM is really quite astonishing. There are no known discrepancies on large scales between the predictions of this theory and the observations. And the predictions are now being tested with amazing precision, as you'll see. So the challenge now is to understand the underlying physics of the dark matter and the dark energy, and also to understand why the proportions are what they are, and to deal with various other questions, some of which I think are philosophically interesting. Like, what is it that we need to explain, and what counts as a suitable explanation? I'll get to that in my next lecture. So this lecture is basically historical. So, in 1933, the iconoclastic but brilliant astronomer Cruz showed that the velocity dispersion, that's what sigma b means, of clusters of galaxies, in particular the coma clusters, the one he studied, are of the order of 1,000 kilometers a second. That means the galaxies are moving with respect to each other with random velocities of that size in each direction. And that meant that there's far more mass holding that cluster together than you can see in any form. In the 70s, people started to realize that something similar is happening with galaxies. Then, by the 1980s, by around 1980, most astronomers were convinced that dark matter exists and is the main form of mass around galaxies and clusters. There was a brief period during which people thought that the dark matter might be like neutrinos, which became known as hot dark matter. The cold dark matter theory was proposed in 1983-84 by me and my colleagues. And in 1992, the first satellite observation of the cosmic microwave background by the Cosmic Background Explorer satellite COBE discovered the CMB, the cosmic microwave background fluctuations, as predicted by cold dark matter. And at that point, there were just 2 versions of the cold dark matter theory that were consistent with both the cosmic background data and also large-scale structure data, namely cold plus a little bit of hot dark matter, and the theory that finally became the sole survivor, lambda CDM, with about 70% of the total energy of the universe in the form of dark energy, and 30% in all forms of matter. There are two questions.
Can you just clarify briefly what cold and dark?
The whole rest of the talk is going to be about that.
Well, I just meant, is that
Cold dark matter refers to particles that are traveling very sluggishly in the early universe. That means very non-relativistically, and by the early universe, let's say 1 minute after the Big Bang. Excuse me, 1 year. Let's say 1 year. 1 year after the Big Bang is a particularly nice time, because that's when the horizon around any spot encompassed a mass of 10 to the 12th solar masses, which is the mass of a big galaxy like the Milky Way, mostly dark matter. You had a question?
I was wondering what was the motivation to bring cold dark matter theory into play? What was the problem with the hot dark matter theory?
That's what the whole talk's about. So what I'm doing here is just giving you a sort of a very big summary, and then I'm going to go piece by piece through the whole story.
What's the lambda stand for?
Lambda was the symbol that Einstein used for the cosmological constant. And more generally, so that's energy that's just associated with space. So it's sometimes called vacuum energy. And I'll explain more about that in a little while. But anyway, more generally, we use lambda to refer to either cosmological constant or something that's like a cosmological constant but possibly dynamical. To really explain it requires some general relativity, which I wasn't going to go into in this lecture. Anthony is going to talk about that in the next lecture, and depending on how much he says, I'll pick up in my next lecture, which will be, I think, tomorrow. So, in 1998, two different groups using type 1a supernovae to measure the distance of things whose redshift was known. So, to get the distance redshift relation, that's the expansion history of the universe. Two different groups, to their surprise, found the same result, which was that the universe has been accelerating for the last 4 billion years. And that was not what they expected. In fact, Martin Rees and I, and two collaborators, had published an article in 1991 discussing in some detail why this was a reasonable expectation and what exactly one should look for. So it didn't come as a shock to many theorists, but at least to some theorists. But it certainly came as a shock to lots of other astronomers. And a lot of other things came together in 98. So I would call 98 is the watershed. After that, the modern picture was basically established. By 2000, it was clear that there was no other alternative and that this picture was really working. From 2013 till actually the present, I should make this 2003 to 2013. WMAP Planck, which just released its results this year, and large-scale structure, LSS, confirm lambda CDM predictions. And maybe we'll discover what the dark matter is. There's a lot of very interesting data that's coming out now that is hinting that we may be on the verge of a real discovery. So now, in much more detail, the early history. Now, in case you're afraid I'm going to go through every one of these papers, I'm not. I'm just going to describe in some detail the ones that I've marked in blue. They're all interesting. There's actually more stuff that I could have put on the list, but time is limited, and your patience, I'm sure, is also limited. But I wanted you to at least get a sense of what's been going on. So there's good old Fritz. Supposedly, what he meant by this is his summary of the total contributions to astronomy of everybody else except him. I'm not sure that's what he meant, but he was pretty cantankerous.
Did you know him?
No, I never met him. He had a big chip on his shoulder, according to everybody I know who did know him, because he had the feeling that people didn't adequately appreciate his brilliant contributions. Not only brilliant, but involving a massive amount of work. What's on the table in these books is his catalog of galaxies and other objects, which was the most extensive observational catalog available before the modern era of computer-aided automatic measuring devices. So in 33, he published a paper in German where he gave that argument I mentioned about the coma cluster. And he said that the material must be Dunkelmaterie, which is just German for dark matter. So he coined the phrase dark matter, and it stuck. And that's what people have called it ever since. Now, here he says that the mass-to-light ratio in the coma cluster, the amount of mass you need to hold these galaxies together that are moving at 1,000 kilometers a second with respect to each other in random directions, is 500. Now, the mass-to-light ratio is always measured in units of the sun, that is, solar mass, which is 2 times 10 to the 33 grams, divided by solar luminosity, which is 4 times 10 to the 33 ergs per second. And so that's called 1. Now, the sun is actually a little more massive than a typical star. And if you take the average of the nearby stars in B band, the mass-to-light ratio is about 3. So a mass-to-light ratio of 500 is more than 100 times greater than the mass-to-light ratio of the visible part of the Milky Way. So he's saying that there's an enormous quantity of undiscovered Dunkelmaterie. See, that's 3 is the local value. The article also proposed measuring the masses of galaxies by gravitational lensing. This was published in English in Astrophysical Journal, the main American astronomy journal, in 1937. And in 1934, Einstein had published in Science, the American journal, the detailed discussion of gravitational lensing, where he pointed out that if there's a galaxy directly behind another galaxy, the foreground galaxy will lens it as a ring, known ever since as an Einstein ring, and various other things like that. And Einstein said in that article that he didn't think that this would ever be observed. And Zwicky said, not only will it be observed, this has become the standard way that we measure the masses of things. Well, it is now. He said it in 37. Zwicky also is the one who first, or certainly among the first, who appreciated that neutron stars should exist, that black holes could form from stellar collapse. I mean, he was a remarkable character. Skipping ahead till the 50s, Kahn and Wolscher at Princeton and the Institute for Advanced Study showed by the following simple argument that the mass of the local group, that is our galaxy plus the Andromeda galaxy, is around 2 times 10 to the 12th solar masses. As I said, what we think is that the Milky Way galaxy has a mass of about 1 times 10 to the 12th, and the Andromeda galaxy also about 1 times 10 to the 12th. So the total is about 2, 1.8 they get. That's very consistent with the modern number. Now their argument was very simple. They said, in the Big Bang, it wasn't yet known that there was a Big Bang, but that was a reasonable assumption. So in the Big Bang, everything was flying apart. How much mass would you need to turn that around and have them come back toward each other with the measured velocity of approach, which is about 200 kilometers a second? And that's the amount of mass you need. Not a very difficult calculation, very straightforward. Also basically correct. So, but nobody paid much attention, because it was only Crazy Fritz, and incidentally, many other people, including the director of the University of California's observatory, Lick Observatory, the first mountaintop observatory, which is now headquartered here at UCSC, they confirmed that other clusters of galaxies had similar random velocities at the order of 1,000 kilometers a second. So there wasn't anything special in that respect about coma. Things got really interesting when the rotation curve of galaxies began to be measured, especially by Vera Rubin and also by Mort Roberts. So this is Vera's data. Her data is actually shown with the error bars. And this is velocity in the vertical axis versus distance from the center in arc minutes. So this would be out to about 20 kiloparsecs, about 65,000 light years from the center of Andromeda. Now notice Andromeda sort of peters out about here, so it required special equipment, the first use of phototubes, to actually measure out as far as this, you know, out in the outskirts. It wasn't an easy measurement. But what was really impressive was that you could actually measure neutral hydrogen even further out, and you found a rotation velocity of about 220 kilometers a second, all the way out as far as you could measure, way beyond where you could see stars. And the fact that it continued flat like this was the indication that there's a great deal of dark matter. The reason is that if the mass is where the light is, and you can see where the light is, it's mostly concentrated there, then the velocity should fall off as 1 over the square root of r. That's what Kepler's law says. 1 over the square root of r. So instead of being flat like this, it should have continued to decline. No one has ever seen a galaxy that does that. Galaxies have flat rotation curves, as far out as you can measure. And so this was a challenge. These guys said, we're theorists. Of course, we expected this. They only wrote the paper after Vera Rubin had already published her results. And they said that the reason that you'd expect that this must be the case, that there's this large component of dark matter, is that a thin disk of stars, or stars and gas, is unstable. Because if it starts to clump, then the clump will grow. On the other hand, if that disk of stars and gas is actually mainly being held gravitationally, held together by very rapidly moving particles going every which way, and the disk itself isn't the main source of its own gravity, mainly the gravity is coming from this other stuff, oh, well then it's no problem. And they said the halo, it's come to be known as a halo, which is very misleading because people think halos are sort of round things. These are actually spherical, not quite spherical, but more or less spherical. Big blobs, denser in the center, less dense further out. So the mass interior to the disk must be comparable to the disk mass. Thus normalized, the halo masses of our galaxy and other spiral galaxies exterior to the observed disk may be extremely large. So in other words, going back to this picture, the mass of dark matter is comparable to the mass of the disk in that region, but then the dark matter continues out very far. So that's why the mass is much larger than the mass of the stars. What's the mass of all the stars and gas that we see in our galaxy? Answer, about 6 times 10 to the 10. So in other words, only about 6% of the mass of the Milky Way, 6 times 10 to the 10 versus 10 to the 12, is in any visible form. And it turns out that's a high percentage. Most galaxies aren't that high.
I take it from what you said that the dark matter doesn't extend forever,
No.
which would suggest that you should see eventually the...
We've seen in great detail, I'm not going to have time to show it all, but since you mentioned that, the velocity falls off as you, what you do is you can either look at satellites or you can use gravitational lensing. So there's now, the Sloan Digital Sky Survey allows us to look at thousands of satellite galaxies around normal galaxies and measure their relative speeds and so on. So what we know is that the dark matter falls off roughly as r to the minus 3 and then a little bit faster as you go further away. R to the minus 2 would be constant velocity. So it's r to the minus 2 and then r to the minus 3 and then even a little bit faster. And the simulations predict this. I'll show you a lot of simulation stuff in my third lecture. And then we actually see exactly what's predicted. As I say, there's just no discrepancies. Every single blessed little prediction, when it's tested, has turned out to be true. Yes?
Can you explain the velocities near the center of the galaxy? So on the graph it looked like it sort of went up and down a bit.
I'm not sure how good that is. I mean, I would want to look at modern data. This is very old. But basically, this happens to be a galaxy that has a massive black hole at the center. Around, it's more massive than the black hole at the center of our galaxy. This is the nearby Andromeda galaxy. known as M31, number 31 in Messier's catalog. And so it has a black hole at the center, it has a big star cluster at the center around the black hole. And so the velocities near that could be quite large, just as they are actually, if you made a similar plot near the Milky Way. The highest velocities are around 1,000 kilometers a second up close to the black hole. I don't know exactly what they were doing there. The point I'm trying to make here is the outer part. This inner part, you want to look at more modern data. So, following up on that paper by Ostreicher and Peebles, there was this paper with their collaborator Amos Yahiel, where they basically just summarized all the available data, including this increasing amount of data on the so-called rotation curves, velocity versus distance in galaxies. The total mass per giant spiral is of the order of 10 to the 12th solar masses. And the mass to light ratio is around 200 for galaxies. And that implies that the total density of the universe in units of critical density, careful explanation of critical density will come, I think, in Anthony's lecture this afternoon. If not, I'll do it in my next lecture. But basically, if you don't have any cosmological constant or other form of dark energy, then there's a certain dividing line in mass density between a universe that will expand forever faster and faster, a universe that will expand forever, always slowing down. A universe that will expand forever at constant speed, that's the high one, and a universe that will stop expanding and collapse. So the expand forever but always slowing down is a very special dividing line. I think I will talk about that later in this lecture. And that corresponds to critical density. That's the special case of critical density. The universe that expands forever, always slowing down. It turns out the equations are identical to throwing a ball up in the air. If you don't throw it too hard, it goes up, it comes down. That's like a collapsing universe. If you throw it really hard, like with a rocket, it will escape, and once it gets beyond reasonable distance from the Earth, it just goes at constant speed, ignoring the effect of other planets and the Sun. There's a dividing line where you throw it exactly at escape velocity, and that's what corresponds to critical density. There, it never stops, but it's always slowing down. Turns out it's exactly the same. It's the same equation, so the same solutions for the universe. Anyway, so what these guys said is that it's not critical density, it's about 0.2 of critical density, about 20% of critical density. These guys, especially Jan Einasto, one of the giants of modern cosmology in Estonia, they particularly looked at the clusters of galaxies. They also looked at the data on individual galaxies, and they again concluded that about 0.2 is the cosmic density. The current number is about 0.31. 0.2, very good under the circumstances. Bill Matthews, here at UCSC, introduced the use of yet another method for measuring the masses of things, in this case clusters of galaxies. So a big cluster of galaxies, the 1,000 or so kilometers per second corresponds to a temperature, because temperature and velocity are just related to each other. The temperature is just like physical velocity squared times a constant. This corresponds to a temperature of tens of millions of degrees Kelvin. And gas at those temperatures radiates X-rays. It's like multi-kilovolt, 10 kilovolt. So the X-rays were observed in the 70s from the nearby Virgo cluster, especially around the big central galaxy in the Virgo cluster called M87. And so you can say, okay, we see this hot gas. How much gravity would be needed to confine the hot gas? And that was the question that Matthews answered. The bulk of the mass in M87 must be distributed in the low-density, low-luminosity component, quite unlike the distribution of luminous matter. This could account for the missing mass in the Virgo cluster. In other words, this mass that Wiki and others had said is there. So the point is, not that we know what it is, but that we are seeing a completely independent test that shows exactly the same thing. We now have results on thousands of clusters. This was the first. So, in 1979, these two people, Jay Gallagher, who continues to run observational consortia, and Sandy Faber, my senior astronomy colleague here at Santa Cruz, published this paper. After reviewing all the evidence, it is our opinion that the case for invisible mass in the universe is very strong and getting stronger. The fact that mass-to-light ratio for binaries agrees so well with that for small groups. So the idea is that by seeing how much mass there is from an argument like that common Vulture argument, the relative velocities of two galaxies, and then in small groups of galaxies. So the mass distribution in the Milky Way local group is reassuringly consistent with other groups. Although such questions as observational errors and membership probabilities are not completely resolved, we think it is likely that the discovery of invisible matter will endure as one of the major conclusions of modern astronomy. Yes?
So it's one thing to say that the dark matter is invisible, and another to say it's very dim.
Well, very dim just means not observed yet.
Yeah.
She's a careful observer, and it hadn't been ruled out that it was visible in some dim component.
People think, right, that dark matter doesn't interact well with anything. So.
Well, the evidence now is enormously stronger.
Right.
It
So
now
I just
looks
wonder when
super,
people start
super
thinking-
deeply. There have been several claims of seeing light from the dark matter. People look more carefully, those claims evaporate.
Right.
As far as we can tell, the dark matter.
Started thinking about really invisible matter versus just not observed yet.
Oh, well, people were thinking about it, certainly before this paper. The important thing is these guys are astronomers. And what's really important is that half the literature was wrong, including papers by people who then or subsequently became quite famous. Typical example. They tried to measure the mass of a pair or small number of galaxies, but they didn't properly take out the galaxies that were just foreground or background interlopers, and would give an anomalously large value for the velocity and therefore the mass that must be holding these galaxies together. And so something like half of the total literature was plagued by this kind of bad science. And what these guys did is they read through every blessed paper. They carefully examined every one. They sort of scored them all. They threw out half the literature. But what was left, they said, we can't see anything wrong with this. And it's all basically telling us the same story. Sandy told me that this is the first paper she ever wrote about dark matter. She'd already been an astronomer for a decade at this point and had written lots of papers, some of which have become quite famous. Something called the Faber-Gallagher relation. The Faber, what's the other name? One of her students. Anyway, it's the standard, it's the most important relation that describes the properties of elliptical galaxies. Basically, the mass of the galaxy is proportional to the fourth power of the internal velocity. Faber-Jackson, right. Jackson's a contractor here at Santa Cruz. He left Santa Cruz and decided he'd rather stay here and not become a professional astronomer. Anyway, so Sandy told me that she preserved her virginity by never writing a paper about dark matter until this one. So she had, no axe to grind. I think Jay Gallagher similarly did not written about this. And being here at Santa Cruz, this made an enormous impact on me. I mean, not just the paper, but conversations with Sandy, who's become one of my main collaborators. So it got me thinking about what the dark matter might be. So by 1980, most astronomers are convinced that the dark matter exists around galaxies and clusters and holds them together. But is it hot or cold? The hot, warm, cold terminology was introduced by Dick Bond and me in our talks at the 1983 Morion Conference. This was the first of a series of French ski conferences, where all day long, there's talks early in the morning and late in the afternoon, and in the middle of the day everybody goes out skiing. This was a great experience for me. I tried to take skiing lessons, downhill skiing lessons, and I kept falling down and getting wet, and I gave up after a little while. And I went inside, and there was only one person who stayed inside during the conference. and that's Martin Rees. Martin Rees is a hunchback, and he doesn't do things like skiing. So all day long, for the entire conference, Martin and I worked on the cold dark matter theory. That was, I'd already done major work on it. In fact, I presented work on it that I'd done with George Blumenthal, who's now the chancellor here at UCSC, and I'll show you some of that later. But filling in the details, Martin was extremely helpful. So, in 1973, George Marks and Alex Allais, and also Kausick and McClellan, showed that the dark matter might be like neutrinos, and that the neutrinos had to have a mass less than 100 electron volts. This is mc squared. And for comparison, the lightest particle whose mass we know is the what? What's the lightest particle whose mass we actually know? You all must know this. No, we don't know the mass of the neutrinos. We only have upper limits.
Light?
Well, yeah, mass is 0. I meant the lightest one that has mass, and we know what the mass is.
Electrons?
The electron. And what's the mass of the electron?
Very small.
Well, no, it's 511,000 eV. In other words, 0.511 kilovolts. Okay? So 100 is a lot smaller than 500,000, right? So, and we now know that the mass of the neutrinos is actually less than an eV. The mass of all 3 neutrinos put together. So neutrinos are very, very low mass particles. They would be moving relativistically in the early universe, meaning at very close to the speed of light. And so, because the temperature at a year after the Big Bang was much, much greater than this small fraction of an eV, even 100 eV. So the net result is that if neutrinos were the dark matter, they'd be hot. Cold would mean having essentially very, very non-relativistic velocities, very small compared to the speed of light. And warm is the intermediate case. And so in 1980, the great Russian physicist Zeldovich, who had led the theoretical part of the Russian atomic bomb project in World War II, at the tender age of about 30, Zeldovich and his collaborators jumped on the idea that the dark matter is neutrinos. And the reason is partly, well, as I'll say in the next slide, because a Russian group in 1980 was announcing that they had measured the mass of the neutrino and it was 30 to 40 electron volts, which would be enough to be the dark matter. However, the dark matter can't be neutrinos. And rather than go through these words here, I'm going to show you what happened. So, some steps toward cosmic structure formation. Back in these early days, in the 70s and early 80s, many people, Jerry Ostreicher, for example, and Jim Misner, you heard about Misner in connection with the talk by Peter Byrne last week, the co-author of the big tome on relativity, Misner, Thorne, and Wheeler. Misner's a former student of Wheeler's. Anyway, so Misner thought that the early universe might be extremely complicated, very complicated geometry. Ostreicher thought that to create structure, you have to push stuff around with explosions. And he kept dreaming up bigger and bigger explosions. Zeldovich and his group assumed that the early universe is very simple. The earlier you go, the simpler it is. Extremely homogeneous, with tiny, tiny fluctuations. And the fluctuations, to make life even simpler, were in all the components together. So if there's light, that is photons, neutrinos, whatever the dark matter is, whatever the ordinary matter is, they all fluctuate together. That's called adiabatic fluctuations. And he assumed furthermore that the spectrum was scale-free. Now what that means is that as each scale enters the horizon, so in the early universe the horizon grows and grows with time. Longer the time, the farther you can see, because light will have had a chance to, and gravity will have had a chance to get to you from further away. As the horizon grows, new fluctuations on a bigger scale are constantly entering the horizon. The Zeldovich spectrum means that the fluctuation amplitude is the same on every scale as it enters the horizon. This was named after Zeldovich, although he was probably the third person to appreciate it. There's a nice paper by Peebles and Hu that discusses it in detail, and also Edward R. Harrison, the American cosmologist, very, very clearly laid out the arguments for it. Zeldovich's paper was very brief. It was a letter, only a couple of pages long, and somewhat difficult to understand. He was the last person to discover the Zeldovich spectrum, and everything's always named after the last person who discovers it. I said that at a talk at UC Irvine, and Virginia Trimble said, I propose to name that Primack's principle until somebody else discovers it. Anyway, so Zeldovich made those simple assumptions, and he initially assumed that the fluctuations were in baryons. Yes?
Why do you, and the others assume the scale?
Sure, of course. I've read all those papers.
Yeah, why?
Basically, you get into trouble on either long length scales or short length scales if that's not the case. See, if you can make an argument that gravity doesn't have any inherent mass to set a scale. And so, if it's not invariant, then there has to be either growing or declining. It has to be a power law. If there's no mass to make some change, then it's just a power law. So it's either growing or declining, the amplitude of the fluctuations as a function of when they come inside the horizon. If it's growing, then with time, then structure will become more and more chaotic on bigger scales. If it's growing as you go back in time, then you're going to turn the universe into black holes at some early stage, which would be catastrophic. So that was the basic argument. I mean, it doesn't prove. Then you have to have some idea of when you can, how far you can carry this argument. How early can you let it go, how late. But that was the basic argument. Yes. Well, later on, inflation predicted this, but this is all pre-inflation.
It sounds like Zeldovich is proposing a structure that's a fractal structure.
As a matter of fact, there's a fractal aspect to it across certain orders of magnitude. That doesn't really follow yet from what's here. I spent a week with Zeldovich and Mandelbrot and others in Budapest in the summer of '87, where Mandelbrot, Mr. Fractal, kept insisting, everything's a fractal. And we astronomers kept saying, no, it's only a fractal over this range. It can't be. He was impossible. Zeldovich, of course, was on our side. Anyway, so first, Zeldovich assumed that the dark matter was just made of ordinary stuff, baryons, in some invisible form. And the problem is that the amount of growth of fluctuations that you could have from redshift of 1,000 when the cosmic background radiation was released until now is only a factor of 1,000 if it's baryons. And you can't have had any significant growth before that, because the baryons are locked to the photons. And that meant that you had to see the fluctuations in the cosmic background radiation when you had a sensitivity of a few parts in 10 to the minus 4, delta T over T, looking in different directions, seeing changes in the temperature of a few times 10 to the minus 4. Well, the measurements got better and better and better. They got down to 10 to the minus 4. Nobody saw any fluctuations in the cosmic background radiation. So you had to give up the idea that the universe is mostly made of baryons, of ordinary matter. Baryons, we call it baryons because essentially all the mass in ordinary matter is in the protons and the neutrons, which are called baryons. It was Abraham Pike who introduced this terminology. Leptons, just using the on Greek ending and the Greek ending lep for light, that is low mass, and bary for heavy. So proton, neutron, are baryons. The leptons, the electron neutrinos, have almost no mass by comparison. The electron's mass is about 2,000 that of a proton. Anyway, so then along comes this Russian experiment, and so they jump on the bandwagon of hot dark matter. George Blumenthal and I really liked the Zeldovich approach. We really appreciated the work of the Zeldovich gang. But we tried warm dark matter, because that's what followed from supersymmetry, we thought, and then cold dark matter, with Sandy Faber and Martin Rees. And of course, cold dark matter, we always said, is something that moves sluggishly in the early universe. And our friends in Santa Cruz knew that that was a call out to our mascot, the banana slug. You actually see these banana slugs all over the place here at UCSC, but only in the wetter months. I don't know what they do in the summer. So this is the paper by Cossack and McClellan, 1973, hot dark matter. Neutrinos with masses of tens of electron volts. They're no longer a good candidate, but the idea of weakly interacting massive particles as the dark matter is now standard. So this was the first paper in a major journal that said that, a National Physical Journal. The Marx and Zalé paper was published in an obscure Hungarian journal, but nevertheless had the same content. So there's Zeldovich and his former student Sergei Shandarin, with whom I had the pleasure of spending a week at the University of Chicago, week before last, at a conference called Galaxies in the Cosmic Web. So they're basically saying here that density fluctuations in the cosmic background, that you'd have seen it if it was baryons. You need something besides baryons. So they say, what about neutrinos? Neutrinos don't interact with radiation, so the neutrinos could develop fluctuations before the universe became transparent. And it's this adiabatic scenario. But these guys did the first computer simulation of the adiabatic scenario with neutrinos. So this is Simon White, Carlos Frank, and Mark Davis. These guys were postdocs with Mark at the University of California at Berkeley when they did this work. And of course, I was in close touch with them. And they showed that the neutrino-dominated picture is ruled out. And I'll show you a little bit later sort of graphical evidence of what they found. But basically, they showed that any version of the neutrino-dominated universe simply doesn't work at all. Well, actually, here it is. So this is hot dark matter. This is cold dark matter. And that's the observed galaxy distribution. This is just the nearest couple thousand galaxies. And this is where our own galaxy cuts across the image. So this is called the zone of avoidance. And so what was done here is to make simulations and examine the simulations and plot them the same way. And what you see is that with neutrinos, what happens is that the neutrinos are moving at the speed of light in the early universe. And so if there's a fluctuation so that this region is a little bit more massive than average, and this region is a little bit less massive than average, the neutrinos over here are just going to stream, and the neutrinos over there, and it's all going to average out. Only after the neutrinos become non-relativistic is it going to be possible to preserve any fluctuations that come through the horizon after they become non-relativistic. And so what happens is that only on some large scale, it turns out it corresponds to about 10 to the 15 solar masses. So in other words, 1,000 times the mass of the Milky Way, including its dark matter halo. Only on scales that big, the scale of clusters and superclusters of galaxies, can you preserve fluctuations in the neutrinos. And then what happens is that the fluctuations will possibly fragment and you might make galaxies, but the galaxies will be very clustered together. Much more so than they're observed to be. So, whole new set of papers. And again, it's only the blue ones that I'm going to talk about. So, this is a fairly recent picture of Martin. I couldn't find a really old one. But he didn't have white hair when I started working with him, and he wasn't Sir Martin Rees. In fact, he told me that this whole honors thing that the Brits like was a conspiracy of the ruling class to keep the intellectuals in line. So after Martin was knighted, I asked him, he said he'd never have anything to do with this. So I asked him about it, he said, well, you know, it really isn't so bad. He's now Lord Rees. He's been the president of the Royal Society and the master of Trinity College. But he's a brilliant astrophysicist, and he continues to be very active in research. So anyway, every galaxy has a concentrated luminous core embedded in an extensive dark halo, They considered omega of 0.2, remember, the same as the Ostreicher, Peebles, and Yahil, and Saar, and Iverso. The dark matter makes up 80% of the total mass. Half the residual gas has been converted into luminous galaxies, so in other words, about 10%. Not so bad. They didn't know what the dark matter was, they didn't know what the fluctuation spectrum was, they couldn't predict the masses of galaxies, but the basic picture is pretty well laid out there, and that's why I wanted to work with Martin. Now, in '82, actually in the summer of '81, Heinz Pagels and I, Heinz was then at Rockefeller University, wrote this paper. And what we did is we said that if supersymmetry is the right theory, it was then a fairly new set of ideas, then the lightest supersymmetric particle in the version of supersymmetry that was then favored was the gravitino. And the gravitino would have had a mass of somewhere around a kilovolt, maybe a few kilovolts. So in other words, a few thousand electron volts, much less than the electron, so around a kilovolt. And the idea in this paper was that whatever the lightest supersymmetric particle is, it's stable. That's true in most versions of supersymmetry because of a conserved quantum number called R parity. So in the early universe, you'll have lots and lots of energy, temperatures very high, lots and lots of supersymmetric Petrels, regular particles, the kind that we know. All the supersymmetric ones will decay into ordinary particles plus the lightest superparticle, and that had better be the dark matter or else supersymmetry is wrong, or at least the version of the conserved quantum number. So that was the point of our paper. And we immediately followed it up by working out what the implications of this would be for galaxy formation. So the gravitino-dominated universe can produce galaxies by gravitational instability while avoiding several observational difficulties associated with the neutrino-dominated universe. So this is also 1982, now in Nature. Our first paper was in Phys Rev Letters. This paper got a response from Jim Peebles at Princeton. And you'll notice that one of the first references was our paper in Nature. Now, what we had done was to consider this kind of warm dark matter particle, the gravitino, with the mass around a kilovolt. What people said is, who cares about that kind of theory? It might be supersymmetry, maybe not. Let's consider the possibility that the mass is much greater than that. So that's cold dark matter. He didn't use the term, but this is the cold dark matter paper. It's again assumed with Zeldovich that the fluctuations are adiabatic, massive weakly interacting particles. Weakly interacting massive particles, was suggested as a name for this by Mike Turner and another astrophysicist. I wish I coined that. My former graduate.
Faulkner claims.
No, he certainly didn't. He called them cosmons. My former student coined the name machos for the alternative possibility that the dark matter is massive compact halo objects. For example, white dwarfs. So macho was a play on whim. That's Kim Grice, who's now a professor at UC San Diego. But anyway, so George Blumenthal was sent this paper as the referee. And George and I read the paper, and we immediately saw that, yes, this is a really good idea to take the mass to be very large, the cold dark matter limit. But the paper had two mistakes in it. Peebles had left out the neutrinos, which are about half the total energy in the early universe, the other half being photons. And he also had actually made a mathematical mistake, and he hadn't got the spectrum right. But we decided we'd accept the paper and then immediately set to work on doing it correctly. And by early '83, we had done the whole thing correctly. Dick Bond and Alex Zale were two others who worked out in great detail this kilovolt or massive neutrino case. So they did the hot and warm case. But meanwhile, George and I were busy working out the cold case. So we're now up to this dividing line between 83 and 84. So this is the paper by George, Sandy, Nee, and Martin. So it's called Formation of Galaxies in Large-Scale Structure with Cold Dark Matter. I think it's the first time cold dark matter appears in print. The dark matter that appeared to be gravitationally dominant, that appears to be on all scales larger than galactic cores, may consist of axions, more on that in a minute, stable photons. So by this time, Michael Dine, now professor at UCSC, and others had suggested a different scenario for how supersymmetry could come into play and how it could solve yet another problem called the gauge hierarchy problem. And in that version, particles like the photino, the supersymmetric partner of the photon, would be the natural candidate, would be the lightest of the superpartners. And those particles might easily have masses of tens to hundreds of GeV, maybe 1,000 GeV, TeV. Anyway, these would have velocity dispersions, random velocities, in the early universe so small that fluctuations of galactic size or larger are not damped by free streaming. This idea where the neutrinos would just stream around and average out the fluctuations. The pre-combination fluctuation spectrum is calculable. Recombination just means when the universe becomes transparent, when atoms form, about redshift of 1,000, about 400,000 years after the Big Bang. And it in turn governs the formations of galaxies and clusters. Good agreement with the data is obtained for a Zeldovic spectrum of primordial fluctuations. Remember, that's when the amplitude of the fluctuations coming inside the horizon is independent of the horizon side. It's always the same. About 10 to the minus 5. So we worked out in considerable detail what the theory would imply. Data had just become available. This was 84. In 83, the first redshift survey was published. 2,000 galaxies. We're now up to about 2 million. But it was extremely valuable data because it let us see whether the sizes of groups and clusters and the distribution of individual galaxies was consistent with this theory, and it was. So these were conclusions from our paper. We conclude that a straightforward interpretation of the evidence favors omega equals 0.2 in the cold dark matter picture, but we couldn't rule out omega equals 1, in other words, the critical density of dark matter. The model predicts roughly the observed mass range of galaxies. This was the first paper that explained why most stars are in galaxies the mass of the Milky Way. There's a special scale, about 10 to the 12 solar masses, and this theory, for the first time, gave us a clear understanding of where that comes from. When I was in college, Feynman's lectures came out, and in volume 1, he has a picture of a galaxy, and he says, if you're looking for a good problem, try to understand galaxies. We do not understand why there are galaxies. I never forgot that. So, a big motivation for this work was trying to understand why galaxies even exist and have that characteristic mass scale. The observed Favor-Jackson-Tully-Fisher relations favor Jackson. The random speeds in galaxies correlates with the mass of the elliptical galaxy. Tully-Fisher, same thing, except now it's the rotation speed of the spiral galaxy correlates with the mass of the spiral galaxy. It also gives dissipationless galactic halos and clusters, just as an agreement with what we see. Dissipationless just means that these particles don't interact with each other. They just go right through each other. In addition, it may provide natural explanations for galaxy environment correlations and differences in angular matter between elliptical and spiral. Finally, the cold dark matter picture seems consistent with observed large-scale clustering, superclusters, voids. Best model available merits close scrutiny and testing, which is what it's received ever since. So this was one of the things I presented in these conferences in 1983 that George and I had already worked out. These are the cooling curves. This is with pure hydrogen and helium, and this is with metals, in other words, all that elements heavier than hydrogen and helium, with solar composition. And this is the number density, so this is the density increasing downward, and this is the temperature increasing to the right, which is the velocity squared, basically. This is the fluctuation spectrum, plotted in this way, where the numbers are a log 10 of the mass of that object. So 10 to the 12 solar masses, 10 to the 13 solar masses. And so what you see is that objects below about 3 times 10 to the 12 can cool, at least if there's some metals around. But objects up here, groups and clusters, can't cool. The gas, if it's in a smaller part of a group or cluster, reaches higher density and it can cool and make a galaxy. So these are the galaxies, the observed galaxies, the ellipticals, the SA spirals, the SC spirals, the irregulars. And this shows the path of a collapsing cloud of ordinary matter inside one of these halos. Its gravity is governed by that of the halo down to here, and then its own self-gravity takes over, and that's why there's a change in slope. And so the idea is that from the fluctuation spectrum, you could understand where all of the different galaxies came from. We had a much more elaborate version of this plot in the published paper that came out in '84. So, to summarize, galaxies have to lie between 10 to the 8 and 10 to the 12 solar masses. The massive ones are going to be a little more than 10 to the 12 solar masses. This cooling function had been worked out earlier. Here, we're plotting density going upward, so the plot is just flipped from before. But the point is that cold dark matter is what gives you this curve. And that's what tells you that the dividing line between galaxies and clusters and groups is about 10 to 12 solar masses. In more detail, this is the growth of fluctuations. This was also presented in our lectures, in my lectures in 1983. So what we did is we assumed this a low spectrum. So what this is the amplitude of the fluctuation, the log of the amplitude of the fluctuation. That's delta rho over rho. So the idea is that you take spheres of a certain size and you plop them down every place, and you measure what the average density is in that sphere. And then for each sphere, you subtract the actual density in that sphere, you subtract from that the average density and divide by the average density. So that's delta rho over rho. Okay? And that has a Gaussian distribution when things are small. And so you can characterize it by giving the amplitude. And so this is the amplitude, the log of the amplitude. And as you see, it's just slightly more than 10 to the minus 5. That would be 10 to the minus 5. And, whoops, and it's the same on all scales. That's a 10 to the 6 solar mass, 10 to the 9 solar mass, 10 to the 12 solar mass. Of course, each one would correspond to a bigger and bigger horizon. So these come into the horizon at these different scale factors. Scale factor. So the universe expands, and we can say how much it expands by saying how much smaller the presently observed universe was at different eras. So the ratio is called the scale factor, A. So here is 10 to the minus 4, 10 to the minus 5, 10 to the minus 6, of course going back to the early universe. And the fact that all of these have the same amplitude when they cross inside the horizon is the Zildovich spectrum. And that makes it really easy to plot this. Now, what this is showing, so as we'll discuss next time, the universe is dominated by radiation. Almost all the energy is in photons and neutrinos, up until about 30,000 years after the Big Bang, which corresponds to a redshift of 3,500, or a scale factor of 1 over 3,500. So, what you see is that this piling up, there's very little growth, only logarithmic growth of the fluctuations, until the universe becomes matter-dominated, and then all the fluctuations just grow linearly with the scale factor, and that gives rise to this characteristic shape of the spectrum of cold dark matter. You'll see that again. So, cold dark matter allows you to calculate the fluctuation spectrum. If you're not following this, and if you haven't had a course on this stuff, you probably will have trouble following it. All you need to know is that there's a very definite calculation that you can do. It's easy to understand why it's happening, and it gives you a certain scale of fluctuations, delta m over n or delta rho over rho. These guys showed, and also Peebles in 84, showed how to do all these calculations with the cosmological constant. Mike Turner, Gary Steigman, it was Turner and Steigman who coined this term WIM, and Lawrence Krauss. And then Davis, Frank, and White, and now with George Eustachiou, figured out how to do simulations of fairly large scale. At about the same time, Anatoly Klipin was doing such simulations of the same scale, 32,000 particles, in Russia, using primitive computers. But anyway, what these guys did is they showed that galaxies form only at high peaks of the initial density field, and that's called biased galaxy formation. And it was based on an incorrect interpretation of their simulations, and it actually set the field back for several years. So on the one hand, they showed how to do simulations. On the other hand, the best simulations you could do with a few thousand particles. Every particle had to represent a galaxy, but most of the mass is not galaxies, so it inevitably was somewhat misleading. And then there were various things that happened after that. But the key things that I want to talk about are the confirmation of the fluctuations in the cosmic background radiation being what had been predicted by the cold dark matter picture. And then this amazing thing that happened in 97, 98 that really was the solidification of the modern picture. So there's all these, actually let me go back, well, too late. Unfortunately, with all the light in the room, you can hardly see what's happening. But what this is a visualization of the Sloan Digital Sky Survey. You see a lot of galaxies lining on top of each other here, but on the sides there are these voids. Now, to get a better idea of what's going on, you have to rotate the image. These slices correspond to regions of the sky that have been mapped. The regions in between are not empty of galaxies, they just haven't been mapped. It looks like slices through a sponge. Now the quasars. Now, looking at the universe from outside, that's the heat radiation of the Big Bang. The different colors correspond to slightly different temperatures. This is the W map data, the Wilkinson microdynamic probe. So the mapped galaxies in white, quasars in blue, heat radiation multicolored. And the music incidentally is by my wife, Nancy Avery.
What is that, the center?
Us. We're the ones who did the mapping. This is the universe as we see it. So cutting that through the middle, you get the cosmic spheres of time, as we call them in our popular book. When we look out in space, we look back in time. The farther away we look, the earlier the light had to have left these distant galaxies to get to us by the present. So we see the galaxies at earlier and earlier stages. So the center is today, us. The next sphere out is 4.6 billion years ago. The light that left that sphere and is now reaching us, when the Earth and the solar system formed. The next sphere out is about 10 billion years ago, when the big galaxies like the Milky Way started to form. These are all images of nearby and more distant galaxies out to about 10 billion years ago. And you see that they all look pretty much like the nearby galaxies, the elliptical and spiral galaxies that we see nearby. But when you look out beyond about 10 billion years ago, these galaxies do not look like nearby galaxies at all. They look elongated and misshapen and odd colors and all that stuff. These are all images from the Hubble Ultra Deep Field. So bright galaxies started to form maybe 500 million years after the Big Bang. And beyond that is the dark ages, the cosmic dark ages, before the universe was lit up by stars and after the glow of the heat radiation of the Big Bang had faded into the infrared so that our eyes could no longer see it. Now, using new technology on a very large satellite in space, the James Webb Space Telescope, we'll be able to peer a little bit further back to that infrared radiation, but that was emitted by those galaxies. But it's going to be very difficult to go back before that with light. However, this whole region can be viewed, structure formation can be viewed with radio astronomy, looking at what's happening in the neutral hydrogen. And that's going to be a huge project for the next decade, culminating in the square kilometer array, a whole kilometer squared of detection. It's going to cost over $1 billion. It will generate an exabyte of data a day. An exabyte is the entire content of the internet now, worldwide. So we'll be processing that much data continuously. That will require processing capability of over 100 petaflops. That's much more than the biggest machine in the world right now. But we'll probably be at the 100 petaflop stage in a year or two. So 10 years from now, it should be duxy. The colors of the cosmic microwave background and the outermost sphere is the Big Bang beyond which we can't see. So we can't look before the cosmic microwave background with light, because the universe is opaque to light before that. It's a plasma. It's like trying to look inside the sun. But neutrinos and gravity waves can penetrate that. We don't know how to detect neutrinos, but gravity waves we actually know how to detect. And over the next couple of decades, there will be experiments that try to detect the gravity waves from before the cosmic background radiation. Partly it can be seen in the cosmic background radiation. The gravity waves actually affect the cosmic background radiation and make a particular kind of pattern called V-wave polarization. But it hasn't been seen yet. So it's straightforward to calculate the distance that the matter is that radiated this heat radiation. So everything is being plotted where it is today. And so the heat radiation is plotted where it is today. And where it is today is 46 billion light years away. Now, to any student who's taken an elementary course of cosmology, this is standard stuff. It's a homework problem. To anyone who hasn't solved that homework problem, this always looks mysterious. How can it be that that stuff is 46 billion light years away when the universe is less than 14 billion years old? Well, the answer is that it's been traveling for much of that time faster than the speed of light. And then there's always somebody who says, but doesn't that contradict relativity? And the answer is, of course it doesn't contradict relativity. This is relativity. This is general relativity. What relativity says is that the absence of gravity and expansion and all that stuff, that's special relativity. Light is the maximum speed. Nothing can travel faster than light. Nothing except light even goes, or any other massless particle even goes at the speed of light. But that's the statement in an inertial reference frame, where the law of inertia applies. Inertial reference frames can expand away from us at arbitrary speeds. The farther away they are, the faster they're expanding away from us. That's Hubble's law. Their expansion velocity is proportional to their distance. So this is perfectly consistent with relativity, general relativity, and it's in fact what general relativity implies. Incidentally, Ned Wright, W-R-I-G-H-T, has a nice website where you can do all these little calculations by just plugging in some numbers into his JavaScript calculator. And somebody else now has created an app for the iPhone, and I think also for Android phones, that does all the same calculations. I have the app on my iPhone. It's called Cosmology. It's of course free. So if you want to be able to calculate things like that, and all kinds of other things about the universe, that's Cosmocal or Ned Wright. And Ned Wright has a nice website that explains all these things. Did you have a question?
You lost me about the frame of reference of relativity.
So the idea
what
is,
frame of reference are we in if the inertial frames are receding?
well, so every place in the universe has preferred reference frame. Special relativity, Einstein in 1905 would not have expected that. because he didn't know about the cosmic background radiation. But the cosmic background radiation actually sets up a preferred reference frame every place in space. It's the reference frame where you're not moving with respect to the cosmic background radiation. How would you know? Well, what it means is you see the same temperature all around you. We, on Earth, are actually moving at about 600 kilometers a second with respect to the cosmic background radiation. We're going around the center of our galaxy at about 200 kilometers a second. Our galaxy is moving toward the Andromeda galaxy. The whole local group is moving toward a certain direction in space. Altogether, we're moving at about 600 kilometers a second on average over the year. With respect to the cosmic background radiation reference frame. So every place in space there's a preferred reference frame. And those preferred reference frames are flying away faster and faster from us the farther away they are from us. Okay? And
So it's the CMB that's the ultimate reference frame.
yes. Okay, anyway, of course this picture of spheres within spheres is reminiscent of the picture that was the standard picture of the universe throughout the Middle Ages, starting with the Greeks and sort of canonized in the Christian and, for that matter, Muslim standard picture of the universe. Jack, did you have a question?
The slide before, I'm a little confused. If we're moving 200 kilometers per second, the whole thing, relative to what? What does that mean to say it's moving 200?
Again, with respect to the cosmic background radiation. So we actually can see how the Earth moves around the Sun at 30 kilometers a second by looking at how the pattern of the cosmic background radiation changes over the year. It's the dipole anisotropy of the cosmic background radiation that used the technical term. It's just because we're moving with respect to the cosmic background. So we see it being blue shifted ahead of us and red shifted behind us in the direction that we're moving. We're moving toward it, so it's a little blue shifted in that direction, a little red shifted in the other direction. We can easily figure out how we have to move to see uniform cosmic background radiation. In other words, no Doppler asymmetry. That's the preferred standard of rest. It turns out that in principle you can actually do that detection for any cluster of galaxies using what's called the dynamic Sunyaev-Zeldovich effect. So this is not just hypothetical, this is very practical. Yes?
I have a question. And about the slices that you showed earlier, you know, the slow needles. Why are there slices even though you can actually see?
It's because they do declination strips. So the way the Sloan survey works is that as the Earth turns, we see, you can keep the telescope at the same, altitude, and then you just sweep across a certain part of sky. And the way that the Sloan Digital Sky Survey works is they've got a bunch of CCDs, and they move the charge on the CCDs at exactly the rate at which they're slowing, that the sky is moving. And so it's a really efficient way to get a lot of data. They have about 100 million images of galaxies. Once they decide which galaxies are the bright ones, in the part of the sky they've surveyed, they then have a machine that punches holes in aluminum plates. Plates are about this big. Each hole has a fiber, an optical fiber inserted in it by a bunch of women. No men have the patience to do this, I understand. The other ends of the fibers are on spectrographs. And so they're now getting, I think, 1,000 redshifts at a time. And then they take out that plate, they put a new plate in. So the Sloan survey, on super clear nights, they measure the brightness of the galaxies and they get images. On nights with a little bit of moon or clouds or something, they collect redshifts. They've now collected over 2 million redshifts. And it's still going strong. The leader of the second phase of the Sloan Digital Sky Survey is Connie Raffesi, who's in our astronomy department at UCSC. UCSC is probably the most important astronomy department in the United States. NASA did a survey of the astronomy departments in terms of their impact and so on, and we came out number 1. Actually, we only came out number 1 when physics was included. I'm actually in the physics department. You have a question?
To the extent that CMB is the preferred frame of reference, couldn't it be inferred that we can find the geographical center or the spatial center point?
No. It's the preferred standard every place in space. There's no place any different from any other place from that point of view. There's no center.
Just open.
Unlike in this picture, where, of course, the center of the Earth is supposed to be the center. Incidentally, the standard picture was to list the planets and the sun and so forth in the order of their how long their period is. So the first thing you get is the moon, Luna, Mercury, Venus, the sun, Mars, Jupiter, Saturn. Count. Saturn is the seventh heaven. Then come the cherubim and the seraphim and God. Okay, so dark matter plus dark energy is the modern theory. So it's based on two dark, that is, invisible components. So in our popular writing, my wife and I have been calling it the double dark theory, and Priya Nagarajan said she likes that, and other astronomers are starting to use this terminology. So it's supposed to be a friendly terminology for our modern picture of the universe, suggesting things like coffee and ice cream, chocolate, of course. So now, this was the WMAP data, the Wilmington Microgravity Probe. The Cosmic Background Explorer satellite only did this part. And this 1,000 figure is just what the cold dark matter theory had predicted. But the cold dark matter theory predicted actually the whole thing. So what this is the power on different angular scales. So it's a way of characterizing the fluctuation in the cosmic background radiation on different angular scales. If you want to know exactly what's being plotted here, raise your hand and I'll tell you. It's complicated, but it's easiest just to think of it as power. Yes? You want to know?
I hate to ask, but I would like to know this.
All right, so what they do is they take the sky and they expand it in spherical harmonics. So you're just taking the temperature and you're expanding the temperature in spherical harmonics. So ALM, YLM, okay, summing on L and M, where L is the principal quantum number and M is the Z quantum number. Just like in that solution of the hydrogen atom or other. So you know what the spherical harmonics? Okay. So you take the ALMs, you take the absolute square, you sum on M, okay? You multiply that times L plus 1, and that's another like 2 pi over something, some constant. That's it, that's the vertical axis. So it's the analog for Fourier transforms of taking the absolute value of the amplitude on different k scales, different wave number scales. So here, L is playing the role of wave number. So the bigger L is, the smaller the angular scale. So on the bottom axis is L, the YLM. On the top axis is converted into angle. The point is, it's a very definite thing. Now, I've oversimplified. One way I oversimplified is that they take out the middle of the diagram, they take out the galaxy. So it turns out that across the middle of this sphere, all the way around, that's the heat radiation all around us. Across the middle lies our galaxy, if you plot it a certain way. The galaxy is a huge source of noise. So they actually take that out, so they actually do it on what's called the cut sphere. And there's a few other simplifications, but I hope you get the idea.
And how do is there an intuitive explanation of the shape of that?
God loves 1 degree. Supposedly Darwin said that God must love beetles because there's more kinds of beetles than there are any other species of plant or animal on Earth. But yes, of course, there's a simple explanation why it peaks at 1 degree. So the fluctuations in the cosmic background radiation are on all different scales. But there's a certain scale where the dark matter and the ordinary matter collapse together. And that's 1 degree. Then they get out of phase and in phase and out of phase and in phase. Why do they get out of phase? The dark matter has nothing to hold it up. once the amplitude is sufficiently large, and the amplitude just grows with time, it will start to collapse. But the ordinary matter has pressure because it interacts with the photon. So all of this is happening before and just at the time that the universe is becoming transparent because atoms are forming. So you have to take into account Doppler effect, and all of that's taken into account. It's a fairly straightforward calculation because it's linear theory. So these calculations were done by my colleagues and me and by other people in the mid-80s.
So we saw a quick path.
So this curve was known to be the prediction of the theory by the late 80s. This part was discovered in 1992. And then we kept saying, well, you just need to have sensitivity at 1 degree and you're going to start to see this. And then, and a lot of people said, you got to be kidding. It's not going to look like that. Every white point and every colored point is an independent measurement.
Is there a simple closed form expression for that curve?
It's not closed form because it involves a lot of calculation. I mean, you have to, it's a computer calculation. Michael?
I'm a little confused in the use of double dark theory. I've always seen this as evidence for dark matter.
Yeah, it's dark matter plus dark energy plus inflation.
How much of that curve, I mean, can you show us what fraction of that curve comes from dark energy? And if so, is
the
this
dark energy plays the role, I mean, the answer is everything.
Well, you could have
And there's a huge literature,
you
there
could
are
have
numerous
two-
review articles
two
where
fits.
in the review articles, what they do is they vary all the cosmological parameters and they show you how this pattern changes. So, for example, if you decrease the dark energy but keep everything else the same, what happens is that this moves from 1 degree to less, the peak. The relative height of this peak versus this peak, which I'm about to get to, I'm nearly finished, the relative height of these two is controlled by the amount of ordinary matter versus dark matter. So it gives you a measure of how much ordinary matter there is in the universe. These higher peaks also, the amount of ordinary matter versus dark matter comes in, but also the dark energy. So the answer is everything is involved, and you have to take into account Doppler effects, and it's.
But it's a pity that there are no two curves, one with dark matter alone and no dark energy.
Ask me
and another
afterward,
curve-
and I'll refer you to the literature that shows all that. I mean, there's nice review articles that
So
make all those plots.
Can one say that this is evidence for dark energy?
It is definitely evidence for dark energy and allows you, just this data alone allows you to calculate the dark energy to within about 10%. You have to throw other evidence in to get it to the current value, which is about 1.5%. So this is using COBE, and then that was superseded by WMAP, which is still up there, but they're no longer taking data. It's had 9 years worth of data now. Question?
Yeah, sorry, you might have already said this. It's just to, so, is this curve including the amplitudes of different oscillatory modes, roughly, is all the CMB itself, or about fluctuations?
This is all CMB, and what this is we take the temperature of the whole sky and basically expand it in spherical harmonics. So you're basically looking at the different angular components. And what you're seeing is that little regions that are 1 degree across are really common. And incidentally, that's about the size of a region that was causally connected at the time that the radiation was emitted, at about 400,000 years after the Big Bang. And there's actually a connection between those two. So anyway, this is the data that was released on March 21st. So it should look very similar, except notice how big these error bars are. And even these error bars from these ground-based detectors at the South Pole. And notice that this only goes out to 2000. Look at that. And the error bars are smaller than the dots. So that's QUANT. That's the European satellite with 10 years later technology. And this is temperature. That is, it's a temperature squared. This is cross-correlating temperature and polarization, and this is polarization. And in every case, the curve was the prediction made way in advance by lambda CDM, including inflation. as I said, there are no discrepancies. This is not an accident. And the same theory also predicts the distribution of galaxies nearby and far away, and it gets that right too. Ward?
Yeah. Is this something about the error bars?
Yes. So what you'll notice is that the error bars get very big here, and also the green region is quite large. And so I put in a little explanation here that that's what's known as cosmic variance. So the idea is that on a 1 degree scale, we have a huge number of 1 degree patches. It's something like 20,000 across the whole sky. So we have, a really good sample. How many patches are we going to have that are 90 degrees across in a sky that's only 360 degrees across? And the answer is very few. The same with 45 degrees and so forth. So the result is that, when we do these calculations, we're calculating an average universe. We're not calculating for our universe, we're calculating for any old universe. We only have a few examples in our universe for these largest angular scales. And the result is that the error bars are fairly large. That's known in the trade as cosmic variance. We have the same problem when we measure galaxies in just a small region of the sky. How representative is that region? It turns out that, because we now have a theory that we can trust, like the CDM, we can actually calculate questions like that. And so the green band is the 1 sigma range. And what you see is that the points are perfectly consistent with that.
Could you explain what you mean by temperature, polarization?
Yeah, so effectively what this is a 2-point function. It's the temperature cross correlation. This is the electric polarization mode cross correlation, different places in space. And this is the temperature polarization cross correlation. So these two are autocorrelation functions, and that's a cross correlation function. And these hadn't been shown before the Planck data. It's a fabulous satellite, and they have instruments now that let us do these things with great precision. And they are equally impressed. So I'm going to read you what they say about this. So remember I showed you that cold dark matter fluctuation spectrum curve that we calculated all those years ago? Well, there it is with the data. And the data comes from many, many different sources. But the data is perfectly consistent with the calculation. That's the cold dark matter spectrum. Smaller than galaxies, clusters of galaxies, superclusters, all the way out to the cosmic horizon. You're supposed to be impressed. So this is the last paper from WMAP, final maps and results. Chuck Bennett is the first author. So they get a non-standard number of neutrino species, 3.26 plus or minus 0.35, well, perfectly consistent with 3. 3 neutrinos, the electron-type neutrino, the muon-type neutrino, the tau-type neutrino. That's all that couples to the Z boson. We measured that at CERN, and the question is, does cosmology agree? They get an age of the universe of 13.77, so round up, 13.8 billion years. The Hubble constant is 69, plus or minus 0.8. So that's about a 1.5% uncertainty. This is the deviation from a Zeldovich spectrum. A Zeldovich spectrum would be 1.0. In fact, it's 0.96. What that means is that there's a little bit less power on small scales than with the Zeldovich spectrum, on the galaxy scale. They measure it on very, very big scales, but now they've got such a big reach, they can measure it at smaller scales. As you'll see, Planck agrees. The inflationary flat late LCDM, lambda CM model, and its precise and accurate parameters rooted in WMAP data, stands as the standard model of cosmology. Now, what is a standard model? we have a standard model of particle physics. We now have a standard model of cosmology, the double dark theory or CDM. What is a standard model? It's a model where we have equations with free parameters. You measure the parameters. These are the parameters. The Hubble parameter, that's the expansion rate in the universe. This parameter, omega. Various other parameters. You plug those parameters in, and you get the predictions that you're seeing. The theory is fantastically overdetermined. We're fitting thousands, literally millions of observations with a small number of parameters, basically 6 parameters. So we can measure the parameters extremely precisely, and there's no discrepancies. You can choose different sets of observations and you get the same parameters. But we have no idea why the parameters have the values they do. And we also don't understand what the parameters describe. We don't know what the dark energy is, we don't know what the dark matter is. So a standard model is a great achievement, but a huge question.
Well, at least you have far fewer parameters than the standard model of elementary particle physics.
Correct. Maybe it's because we know less.
Just clarification, were you wanting to roll in inflation into lambda again as the standard model, or was that?
Yes, it's part of the theory. It was, back in 1984, we said explicitly that we're assuming an inflationary star. And it's always been like that ever since. All that means is that the fluctuations are either exactly Zeldovich or close to Zeldovich, and they're a Gaussian random field. That's all we really want to take from inflation. Well, there's a couple of little details we take from inflation also, but basically it's sort of a generic inflation. Yes?
So on the last slide, you said that they measured the number of neutrinos to
Yeah.
customize the number
Yeah,
of species. I was wondering if you could say a little bit more about how they do that, because I thought that the number of generations of leptons was sort of up in the air. We know that the tau is pretty heavy, but maybe there's something a lot heavier that would have a corresponding neutrino.
Right, and there might also be what are called sterile neutrinos that are in the universe but don't couple to the Z boson. The Z boson doesn't decay. We can easily measure how, it's called measuring the width of the Z. If that is meaningful, great, and if not, it's a separate little lecture to explain what's involved. But basically, we can tell how much room there is for neutrinos. And the answer is 3.0 plus or minus, I think, 0.1 or something. So that's how much room there is for things that couple to the Z, that the Z could decay into. There might be neutrinos that are too massive for the Z to decay into. Z is a mass of 92 GeV, so anything more than half that, the Z could decay into a pair of them. And it's also possible that there are kinds of neutrinos that the Z doesn't couple to. Those are known as sterile neutrinos. The Z boson is like the W boson, the carrier of the weak interaction. In case you didn't know what the Z is. Anyway, so the point is that the cosmic, those figures with the big wiggle, they're sensitive to everything. They're sensitive to how much stuff there is in the universe. The more stuff, the faster it expands. So Big Bang nucleosynthesis is also very sensitive to this stuff. And so from Big Bang nucleosynthesis plus the WMAP or now Planck data, you get pretty accurate measurements, and as you'll see, Planck did better. So omega matter is 0.315, so it's a little higher. It's close to 30%, a little bit above 30%. These guys, I didn't quote what they said, but they're at about 0.29. I guess the number of effective degrees of relativistic freedom, it's very similar to what, so it's 3.3 plus or minus 0.27. Their upper limit on the sum of the neutrino masses is 0.23 electron volts. They're an excellent agreement with Big Bang nucleosynthesis, and the standard value 3.046, that's from measurements at accelerators. And then the unusual shape of the spectrum in the multipole range 20 to 40, L of 20 to 40, was seen previously in the WMAP data, and is a real feature of the primordial CMB anisotropies. the poor fit to the spectrum at low multipoles is not of decisive significance, but it's an anomaly in an otherwise self-consistent analysis of the Planck temperature data. So here's the anomaly. This is the average. You see these down here that are all slightly below average from 20 to, well, I say 40. It's really 20 to 30 that's concentrated in. So that's the anomaly. If you've been hearing that WMAP and Planck have a slight problem, there it is. It's not a very big deal. None of these is more than, I mean, this one is maybe 1.5 sigma. But it's coherent across several multipoles. I don't know what to make of that. Next lecture, I'm going to give you a few other examples of these anomalies, weirdnesses, things. It's not clear if they're telling us something interesting or they're just small fluctuations. Here what I'm doing is showing you the evolution in our value for the Hubble parameter, the expansion rate in the universe. So there's the Planck value, and there it is, 67.3. So if you remember, WMAP said it was 69, and a direct measurement said it was 73, plus or minus 3.5. So there's the direct measurement. The HST key project. So the Planck value is a little smaller. The universe is expanding a little less rapidly than these earlier things said. It's very consistent with WMAP within the errors. It's not terribly consistent with these guys, but it's only a little over 2 sigma away. 2 sigma, well, the chance of being 2 sigma away is 5%. 1 in 20. Except, of course, what could have happened is that they didn't get the systematics quite right. The two most important parameters for a large-scale structure are the amount of mass in the universe as a function of critical density, omega matter, and sigma 8, which measures the amplitude of the fluctuations. And this is WMAP 5, WMAP 7, WMAP 9. These are the 5-year, 7-year, 9-year. This is another recent measurement based on the Baron acoustic oscillation spectral survey. That's the Sloan Digital Sky Survey. This is Bolshoi. That's what has been the world's best simulation. Priya Nandarajan called it that. That's by my group. But Planck is sufficiently different, and the error bars are so small that we felt we had no choice, but we had to rerun the whole thing over again. And it's within about a day or so of finishing on NASA's biggest computer. We were told we could only use their facilities until July 1st. So we've cleared off the disk, we've archived everything, we've moved stuff, partly to here at Santa Cruz, and the thing is still running, and we hope it'll finish today. So this is all kinds of other observations, and you can see it's all pretty consistent, but Planck is a little bit off. This was the other simulation that people often use. Priya mentioned that, the Millennium simulation. And the Millennium simulation was the best simulation available when it was done in 2004, 2005. But it's more than 8 sigma away in both of these axes from what Planck says. So it's no longer close enough to reality.
Could you repeat again what sigma 8, what is the physical meaning of sigma 8?
So what sigma 8 is the amplitude, delta rho over rho. So the average RMS fluctuation amplitude on a scale of 8 H inverse megaparsecs. Jim Peebles, using data that was collected at Lick Observatory, found that if you plop down spheres of 8 H inverse megaparsecs and you count galaxies, that actually, this is using the first redshift server that became available in 1983, the CFA1 redshift server. If you plop down spheres of 8 H inverse megaparsecs, so H inverse, that just means that you divide by the Hubble parameter in units of 100 kilometers per second per megaparsec. So it's about 0.7. So 8 divided by 0.7. So about 11 megaparsecs. So spheres of 11 megaparsecs. You plot, and you determine what the fluctuation amplitude is between the different spheres. You know, the RMS fluctuation amplitude. That's sigma 8. And it turns out it's close to 1. It's close to 1, but it's, as you see, a little less than 1. So it's 1 for the galaxies, at least that's what people found years ago. For the dark matter, it's a little bit less.
I think the spheres are non-overlapping.
Yeah, it doesn't matter. Just lots of random spheres.
Random.
Random. Yeah. I mean, in practice, you're doing a Fourier type of analysis, but that's a way of describing it. So, I'm just about finished. I hope this way of doing things where there are lots and lots of questions. Questions are great. That's the whole point of doing this as a lecture, rather than having to read this in the textbook. So, more questions, the better. Yes?
So can you explain Fourier acoustic oscillations?
I will, but next time. Basically, well, actually, see this big bead here? That's the big baryon acoustic oscillation. Each of these is another one with baryon acoustic oscillation. That's reflected in the distribution of galaxies. We see the same thing in the distribution of galaxies. And it corresponds to a certain length scale in the distribution of galaxies. And so, by measuring that length scale at different eras in the universe, we can measure how much the universe has expanded since then. So it's a way of getting the expansion history of the universe independently of supernovae. So I mentioned that using the supernovae in 1997-98, two different groups determined that the universe was accelerating its expansion. This is a different, completely independent, relatively difficult to, I mean, this is a method that's pretty easy to analyze, because it's really straightforward. And lots of different groups are now using that to try. What we want to do is we want to measure the effect of the dark energy, preferably to a percent, as far back as we can. Certainly back to a redshift of 1, when the universe was half its present size. And so that's one of the best methods of measuring. But as to exactly how it works, I've got some nice slides that I was going to show next time. So there's 5 different ways of measuring the amount of ordinary matter in the universe, baryonic matter. Question before I get to that?
Well, you may be getting to this just now, but last week Priya sort of gave us a soundbite that trying to understand the amount of dark matter and dark energy, relative amounts having different impact at different times in the universe.
Right.
And can you say a little bit more about that, because I didn't really quite get that, and how it would affect. I mean, I think that relative height you said was was impacted by the relative amount of dark matter and dark energy.
Exactly. So that's why I'm saying there are 5 different ways of measuring the amount of ordinary matter in the universe. And this way, you're doing it at 400,000 years after the Big Bang, when this radiation was emitted. And basically, it's just been redshifting since then. So, and there, it's this interplay between the dark matter, which always wants to collapse, and the baryons, which sometimes are in phase and sometimes out of phase. And this actually comes from a much earlier era. This is the first 3 minutes, or more precisely about 10 minutes. So this is the Big Bang nucleosynthesis era. And the amount of deuterium turns out to be the really critical thing. And the amount of deuterium is about 3 times 10 to the minus 5. Number of deuterium atoms per hydrogen atom. And it's been measured a number of different places. And I'm going to talk about that a little bit next time. And absorption of quasar light by neutral hydrogen, that's another way of measuring how much. And this is back at redshift 3, when the universe was 1/4 as big as it is today, 1 over redshift plus 1. So that corresponds to about 2 billion years after the Big Bang. So 3 minutes, 400,000 years, 2 billion years. This is contemporaneous. This is X-ray radiation from the coma cluster. And that tells us how much ordinary matter there is in the coma cluster, because it all lights up. Either it's a gas and it's radiating X-rays, or it's the stars and the galaxies, so we can see it all. And then there's the wiggles in the galaxy power spectrum. And as I said, next time I'll go into that in a little more detail. So the wiggles correspond to actually detecting excess galaxies. If you're sitting on a galaxy, there's more galaxies at about 100 megaparsecs, about 400 million light years. There's an excess of galaxies at that distance around any galaxy. Believe it or not, it's really true. It's a very strong signal. And similarly to earlier epochs. So this is the ultra deep field. And if the lights were out, and if we darken the room, it's gorgeous. You can see 10,000 galaxies here in this tiny little region, which if you take tiny needles, little tiny sewing needles, hold them at arm's length and cross them, that's the size of this region. And then you just multiply 10,000 times the ratio of that tiny little region to the whole sky, and you find that there's about 100 billion galaxies. But you're only seeing, in all the stars and all the dust and gaseous nebulae and so on, you're only seeing half of 1% of the cosmic density. So, in our popular books, my wife and I use this symbol to represent the visible matter. This is hydrogen and helium. Out of the Big Bang come just hydrogen and helium, 3/4 helium, 1/4 hydrogen by, 3/4 hydrogen, 1/4 helium by mass. The first stars are just made of hydrogen and helium. They make everything else. The entire periodic table is made by stars. A little bit of helium and all the rest of everything else, except a little bit of lithium comes out of the Big Bang. This is the whole picture. So of course, this picture, top part is borrowed from the back of the dollar bill, the Great Seal of the United States. The eye represents the fact that intelligent creatures, us and any others, have to be made of the 2% of the visible stuff that's made of heavy elements. So the heavy elements, that's 2% of what's visible, but what's visible is only half of 1%. And so the heavy elements, the metals, as we astronomers call them, are the rarest thing in the entire universe. They correspond to 1/100%, 10 to the minus 4 of the mass and energy density. It's mostly invisible atoms, about 4%. The visible part, remember, is 0.5%. So altogether, it's about 4.5% atomic matter. Cold dark matter, about 25%. Dark energy, about 70%. Latest numbers, this goes up by, it's about 26.5%, and this is about 68.5%. And that's the Planck numbers, and I don't expect there's going to be much after Planck, because there's no more, it's the most sensitive and accurate satellite we have. Here's a somewhat more romantic version. So I don't know if you can see, but there's the pyramid again. There's the bottom part of the pyramid, 70% dark energy. And then the ships, cold dark matter, 25%. Invisible atoms, 4%. Visible matter, 0.5%. Imagine that the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. But you don't see the ships and you don't see the ocean. All you see are the beacons of light at the tops of the biggest masts of the biggest ships. Those are the galaxies.
What are you referring to as invisible atoms here?
Well, as I said, we have 5 ways of measuring the amount of atomic material in the universe, and they all give the same answer. It's about 4.5%. Only 0.5% is visible, and stars and galaxies and so forth. Nebulae, stuff that absorbs light like dust. So altogether, 4% has to be invisible. Where is it? We don't know for sure. It's one of the big issues in modern astronomy. We've located a substantial fraction of It seems that a lot of it is in the outskirts of galaxy halos. It's in a diffuse ionized form, so it's very hard to detect. And the rest is out in between the galaxies, not stars, not lit up by stars.
But it's just very
It's ordinary matter. And as I say, we can measure it, we can measure the amount at many different epochs in the history of the universe, starting with Big Bang nucleosynthesis, from the deuterium abundance that we measured later, but that was produced at Big Bang nucleosynthesis. Deuterium's only destroyed in the universe. There seems to be no way to produce it. It's the most loosely non-revolving gas. So the best guess is that the ordinary matter is just, the 4% that's invisible is just spread out. I'm just about finished. So there's lots of ways that we hope to be able to detect the dark matter. I'll talk a little bit about that next time. There's direct detection. This is the cryogenic dark matter search experiment, which has reported about 3 sigma evidence that they've actually seen something. There's production at the Large Hadron Collider in Geneva. They haven't made it yet, but they've shut down and they're going to upgrade the energy by a factor of 2. And we hope that they're going to have enough energy to start making supersymmetry particles, which will then decay into the dark matter particle, if that theory is right. Naturally, I hope that theory is right because I proposed it. But we aren't going to know until we know. And then this is indirect detection. So you detect particles that might be produced by the decay or annihilation of the dark matter particles. Well, I don't know how many of you have heard about it, but there's 6 sigma evidence, so it's incontrovertible evidence, that coming from the center of the Milky Way, there's about 130 GeV gamma rays, which are being detected by this satellite, which was built here at UCSC. And it has the distribution that's predicted for dark matter annihilating in the center of the Milky Way. So 2 dark matter, this is what was expected if the dark matter is a supersymmetric limit. 2 of them come together and they can annihilate into ordinary matter. Remember, every single one of them is stable. But if 2 come together, then they can turn into ordinary matter. And so, interesting question. If you look at nearby clusters of galaxies, biggest concentrations of dark matter in the universe, do you see the same signal? Answer, yes. It's a 3 sigma detection, so the chance of it being just a fluke is less than 1%. The Fermi satellite team has, I think, decided that they're going to focus on the center of the galaxy. They're going to put a lot of their effort, instead of scanning the whole sky, they're going to spend much more time focusing on the center of the galaxy to try to understand exactly what's going on. So there's lots of hints that interesting things are happening. Whoops. Well, that was going to be my last slide. So I was supposed to say, with all these upcoming experiments, the next few years will be very exciting. Oh, actually, there's one more last thing that I was going to do. Would you like to hear a rap? So, this is David Weinberg from Ohio State University, and he recorded this, and this sort of summarizes this lecture.
Sweet snack can be kind of slippery. The song had better stop. I give it my yard. If anybody says I said in 1933, there's a common loss. The races of the galaxies and lots of people.
So this is a summary of this lecture.
There must be missing mass. Dark matter. Dark matter. Do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it? For nearly 40 years, the dark matter problem sits. Nobody is worried because it only raises risks. The next step's not till the early 1970s. After Cruz dynamics of the galaxies and hold its instabilities. They say with the mass to sit in the star, all those 50 spirals ought to be bars, self-gravitating disks, only know what those spirals mean is a massive halo. And hey, look over here, check out these observations. Zero movements optical curves of rotation. They can provide our needed confirmation. Those curves aren't falling their laps. Dark matter's where it's at. Dark matter, do we need it? What is it? Where is it? How much? What is it? What is it? What is it? What is it?
We still don't know.
And so the call goes out for the dark matter candidates. Black hole cobalt gas clouds, low mass other planets, but we quickly hit a snag because galaxy formation requires too much structure in the background radiation. If there's only baryons and intergalactic fluctuations, the Russians have an answer. We can solve it in-house. Emo has shown the neutrino as mass. Although it tries time, the dark matter's up. Carlos Frank, Simon White, Mark Davis say, not. Quasars are old and the pancakes must be young. Falling from the top down, it can't be done. So neutrinos just a skids and the picture's looking black. But California laid back, doing all Primack, it don't have a heart attack. There's lots of other particles to treat the physics out of it. Take this period it's called supersymmetry. What better for dark matter than the LSP? The mass comes in at a twiddle KPD, and that's not hot, that's war. Jim Peeble says, war, don't be half-hearted. Let's continue to dread what we have started. I'll stake out a position that's bold. Dark matter's not hot, not warm, but cold. The cold dark matter has a overnight sensation and waiting calculations, computer simulations, detailed computations of the background fluctuations. Results are good and the prospect looks bright. Here's a theory that works. Well, maybe not quite. Dark matter, do we need it? What is it? Where is it? How much? Where is it? How much? Where is it? How much? We have another puzzle that goes back to Robert Dickie. Finding a solution has proven kind of tricky. The CMB so smooth, it's as if they're famous contact between parts of the universe that often causal contact out of group says inflation will be our salvation. The smoothness of the universe a causal explanation, and even make the galaxies from quantum fluctuations. There is one prediction from which it's hard to run. If inflation is correct, then omega should be 1. Observers say, stop, no, sorry, won't do. Check out these clusters, omega's 2. The theorists respond, we have an explanation. The secret lies in bias, galaxy formation.
This is when you set back and feel for several years.
Just some regions are missing luminosity. Observers roll their eyes and they start to get annoyed, but the theorists reply, there's dark matter in the void. Dark matter, do we need it? What is it? Where is it? How much? Do we need it? Do we need it? Do we need it? Do we need it? Along comes Motion Milburn, who's here to tell us all this dark matter flat has got you on the wrong track. You're all too mild in conventionality. Wedded to a standard theory of gravity, seduced by elegance, general relativity. Just change your force law, that's the key. Give me one free parameter and I'll explain it all. Not so, plain late, when Spergel et al. On dwarf galaxies, your theory does fall. The argument degenerates, it's sooner bar and brawl. Dark matter, do we need? What is it? Where is it? How much? What is it? What is it? What is it? What is it? New observations hit the theory like an ice-cold shower. They show that cold dark matter has too little logical power. Says people's cold dark matter, not Eva's innovation. An overly aesthetic, theoretical aberration. Our theories must have firmer, empirical foundation. Said all this extra baggage, including the carotons and particles we know, i.e. the baryons. Others unconvinced, and a few propose a mixture of matter, hot and cold, perhaps with strings of texture. Nowadays, some physicists are beginning to wonder if it's time to resurrect Einstein's greatest blunder by keeping exotic particles instead of just assuming that dark matter's all around us. It's what we call the vacuum. Who's right? It's hard to know. The observation or experiment gives overwhelming evidence that theories are predicament. The search is getting popular as many realize that the detector of dark matter may well win the Nobel Prize. So now you've heard my lecture, and it's time to end the session with the standard closing line. Thank you. Any questions?
Okay, well, end of this lecture, unless there's some questions.
So, incidentally, this was 1992 when David Weinberg gave this summary. And so people were certainly thinking about the cosmological constant as a major component of the universe way before 1997, 98, when the observational teams announced that that had been discovered. There was a question, I think? Yes.
So we know that the universe is accelerating because bodies are moving away with increasing speed. So how are we going to measure the real expansion of space-time when it exceeds the speed of light if we can't see the bodies moving faster than that?
Well, first of all, in order to measure the rate, you don't have to measure the most distant ones. You actually want to measure some fairly nearby ones. Not really nearby, because really nearby things aren't even expanding away from us. They're coming toward us, like the Andromeda galaxy. But once you get reasonably far away, as far as the Coma cluster, Coma cluster is receding from us at 7,000 kilometers per second. For example, 10,000 kilometers, 20,000 kilometers a second. There's loads, there's tens of thousands of galaxies that are, whose velocities have been measured. And all we need to do is measure distance and get velocity. And then we get the expansion history. And then we do the same thing a little further away. We don't have to, we can go really, really far away. But also, actually, there was a question that I didn't respond to adequately, which is related to this. So it has to do with the effect of the different components at different times. So if the dark energy is just a cosmological constant, that's really easy. It's just a property of space. The more space, the more of the stuff there is. The more dark energy there is. Now, space expands. But the amount of ordinary matter and dark matter doesn't increase. It gets more and more dilute as space expands. Careful. It doesn't mean that our galaxies expand. The regions that are held together by gravity aren't expanding. In fact, in many cases, they're contracting at this stage of the universe. Like a local group of galaxies where the two big galaxies are coming together. So, regions that are bound gravitationally do not expand. But the distance between them expands, and it's expanding faster and faster. And the way we can tell it's expanding faster and faster is we measure what the expansion rate was at different eras by measuring this redshift distance relation. Redshift is simple. Anytime you've got the spectrum of a galaxy, you just look for characteristic lines, and you see what their wavelengths are, and the redshift is just the difference between what you observe and the laboratory value divided by the laboratory value of the wavelength. Lambda observed minus lambda emitted over lambda emitted. That's redshift. So that's directly measurable. It's easy to measure. You can often measure it to 4 significant places. No problem. Distance is tough. But we have a lot of methods now that we can use to measure distance. And they're cross-checkable. One is these type 1a supernovae, where they're basically equally bright. They can be corrected. There's a thing you can measure that allows you to put all the supernovae on the same scale. So by measuring how bright they appear to be, you see how far away they are. Because the light falls off as 1 over r squared. Anyway, that was the first method that was used. There's now several other methods that have cross-checked it. They're all giving the same answer. The cosmic microwave background gives the same answer. It looks like it's just a cosmological constant, but until we can measure it to better than about 10% nearby, 50% of redshift 1, which is where we are right now, we can't really tell. As you go back in the universe, the ordinary matter becomes more and more concentrated. And therefore, the effect of the dark energy is less and less. So it becomes harder and harder to see the effects of the dark energy at earlier times. But if we see any deviation from this absolute constancy of the amount of energy per unit volume of the universe, that would mean that it's not the cosmological constant, it's something else. Something more interesting, something that could change in time or in position or both. So, since it's the main component of the universe today, and it's, as you're going to hear, it plays tremendous important roles in trying to understand the fundamental nature of the universe. Lenny Susskind, who's going to be lecturing later today, and then again on Wednesday and Friday, has said that if the cosmological constant is real, that absolutely kills string theory. You can't have string theory, superstring theory, and a cosmological constant. That is a controversial position, and another one of the world's experts, Tom Banks, in our physics department here in Santa Cruz, disagrees with that. Never a very friendly disagreement, but they absolutely come out on opposite sides on that question. But the point is, it's really important to figure out what the cosmological constant or dark energy is. And it's doable. I was a senior cosmologist on a National Academy of Sciences study called the Beyond Einstein study. And we said it was the most important thing for the physics community, the astrophysics community to do. It's the most important project for the government to fund. And then, that was in 2007. And then in 2010, every decade, there's what's called a decadal study, where the astronomers get together and make a list in priority of the most important projects. And guess what was number one? The same thing. They renamed it, they called it W-FIRST, Wide Field Infrared Space Telescope. It was the same thing. And then what happened is, the National Security Agency gave NASA 2 spy satellites. All you have to do is turn them around and point them up and put some proper cameras on them, and they become much more powerful than Hubble Space Telescope. They would be a fantastic W-FIRST. So NASA asked a bunch of astronomers to come and figure out, how they should be built and how much it would cost, and the answer is about $1 billion. Which may seem like a lot of money, but Hubble Space Telescope has cost over $8 billion. And James Webb Space Telescope is going to cost well over $8 billion. So, partly because the National Security Agency did the astronomers such a favor and gave us these free spy satellites, the general view is that as soon as NASA finishes spending money on James Webb Space Telescope in about 3 or 4 years, they're going to switch over and take a little bit of the money and start working on W-FIRST, which will be the best way, I think, to measure the dark energies. But in the meantime, Europeans have already made $1 billion commitment to a satellite they call Euclid. And that's going to launch somewhere around 2019. So, meanwhile, there are massive programs using big telescopes on the ground. There's something called the Dark Energy Survey, using the Blanco telescope in Chile. There's another survey called the Virus Survey, using the Javi Everly telescope, a 10-meter class telescope at McDonald Observatory in Texas. And there are others. So we're going to make progress on this question, and we may actually get an answer sometime in the next decade or even earlier. Yes?
Do you have an estimate for the amount of fractions and stuff in the universe which actually forms life itself?
Well, it's certainly only a small fraction of the heavy elements, and as I said, the heavy elements are 1/100%. So 10 to the minus 4 of the mass and energy density of the universe is the stuff that could make planets like Earth and creatures like us. Even I told you that there's an upper limit on the mass of all 3 species of neutrinos. An electron neutrino plus muon neutrino plus tau neutrino of 0.23 of an electron volt. Well, there's also a lower limit, and that's about 0.1 electron volt. So we're closing in. And what that means is that the neutrinos actually make a bigger contribution to the energy density of the universe than the heavy elements do. We are made of the absolute rarest stuff in the universe. We and rocky planets like Earth.
Are you going to discuss the cosmological constant in the next lecture?
Yes, I will. Good morning.
One reason there's a huge discrepancy in its magnitude.
Right. 110 to the 120, yes. I think actually Anthony's going to talk about that in the lecture this afternoon. And very likely Lenny Susskind also. But if they don't, I've already got some slides prepared. So, sure. As I said, back in 1991, Martin Rees and I and 2 of our junior collaborators published the first serious paper on what the dynamical effects of a cosmological constant would be, including how it changes the growth rate of fluctuations. So we took it very seriously, long before the observers knew that it was there. Yes?
Do we know why dark matter has a halo structure?
Yes, what?
Has a halo structure?
Oh, yes, yes. I'm going to show you in great detail how that happens. I'll give you a simple hand-waving explanation next time, and then I'll show you what the computer simulations do. But, yeah. The simple explanation was actually created in 1967. 67. Long, long ago. By one of the great giants of modern astrophysics, Donald Lyndon. And he called it, with characteristic British humor, violent relaxation. That's the technical term, violent relaxation. I once asked Donald if he meant that as a joke, and he said, sort of a smile. No, I meant it literally. Anyway, so what he showed was, by a sort of a thermodynamic type calculation, that if you just let particles fall together, in one free fall time, they distribute themselves in a configuration that basically lasts forever, and that has this property of having roughly constant velocity. That's violent relaxation. And that's what happens when we do computer simulations.
I don't recall, but it seems, are they now at the physical limits on the mass and interaction of the so-called dark matter particles?
Well, we're starting to actually detect the dark matter particles interacting with apparatus, if that's in fact what they're detecting. And so the answer is that we're getting these hints, but you know, the usual rule in particle physics is that unless it's 5 sigma, you don't take it seriously.
So my question is, for the astrophysical data that you have shown us, does that give any limits, bounds on the mass and the...
No, not really. The axion, the preferred mass of the axion, which is a perfectly good dark matter candidate, is 10 to the minus 6 electron volts. The preferred mass of WIMPs is tens to hundreds or maybe even thousands of GeV. In other words, tens to thousands of times the mass of the proton. Both would be cold dark matter. All we know is that dark matter behaves in this cold way. We do not know what it is. There are some interesting additional things to be said, but it's pretty technical and they're not terribly convincing. Yes?
Does anyone have any hunches about what's responsible for the deficit in the low power spectrum?
Oh, you mean this from a scale of roughly 20 to 30 L?
Yeah.
There's probably 100 papers now.
Okay.
So the natural thing is you just play a little game with inflation. So back in 1990, I guess it was, Lev Kaufman, Zeldovich's one of Zeldovich's 2 last students, and George Blumenthal and I and our then postdoc Hardy Hodges wrote a paper that people dubbed designer inflation. And we showed how you could get essentially any shape in the fluctuation spectrum that you like by making appropriate adjustments to the inflaton, the particles responsible for inflation, its potential. And so it's a very straightforward issue. If you want to cause a little bit of an anomaly on a certain length scale, you can build that into inflation. See, the trouble with inflation is it's generic. It's not one theory. It's an infinite class of theories. You just fill it with your parameters and you can have any inflation theory. And that's with one inflaton, but there can be more than one inflaton. And interesting things happen if there's 2 inflatons that interact with each other. You get what's called a waterfall effect. And Kaufman also wrote papers back in those days with Andre Linde, who's at Stanford. And so there are many, many different, there's at least 1,000 different papers on inflation, probably several thousand at this point. So many, many things are possible, most of which have no observable consequences. But if you see some little anomaly, of course you can build it into your inflationary fluctuation spectrum. So inflation doesn't necessarily predict the Zeldovich spectrum. In fact, to get an exact Zeldovich spectrum is really tricky. So you can make the simplest possible inflation model. a scalar field, the inflaton, interacting with itself with a mass term. And that turns out to give you basically what the observers see. Another natural case would be an inflaton interacting with itself with a 5⁴ term. The standard example of a scalar field theory, they usually put in a 5⁴ term as well as a mass term. And it turns out that's now ruled out. This observation that the deviation from the Zoldyck spectrum, where n sub s would equal 1, is actually 0.960. So that essentially rules out whole classes of inflation theories. So we're beginning to zero in, and if we can actually see, maybe there's this little wiggle, that corresponds to the angular scale L equals 20 to 30. That would be a big clue. And, cold dark matter was, a pretty obvious idea, frankly. Inflation is a pretty obvious idea, but once you work out inflation, there's a zillion different possibilities. None of them looks particularly attractive, except maybe these super simple theories with a single scalar field with a single interaction. But maybe if we just get one more clue, like this anomaly, maybe that's going to be the key. The trouble is, maybe it's just a little fluctuation. It just corresponds to the fact that we look at a particular universe, not an average universe. That's a big problem in cosmology, from the fact that we only have one universe to look at. And as I said, I'm going to give you examples of things that will blow your mind. They're so anomalous. But do we take them seriously as something that we need to explain? Or do we just dismiss them as, yeah, all right? I don't know the answer. There's a lot of this. Another name for this anomaly issue is fine-tuning.
You gave nice evidence that dark matter can be confined around galaxies and so forth. What about dark energy? Is it confined within?
People have tried to find any evidence that the dark energy has any change at all in space or time, and they found nothing. All we have are upper limits. But absolutely, you can make dark energy theories where it's a scalar field. And it could very well be interactive with the ordinary matter. There's lots of papers that suggest this.
But there's no evidence for it. Any confinement?
No. But, I mean, again, measurements at this stage are at the 10% level nearby, and 50% level when the universe was half its present age, which is pretty terrible. We know we can do a lot better. So once we do a lot better, maybe the whole situation will change. Incidentally, I like to remind my liberal physics colleagues, I'm politically liberal myself, that if George H.W. Bush had been re-elected rather than Clinton, we'd know the answer to a lot of the particle physics questions, because the Large Hadron Collider would not even have been built, I think. The U.S. was building a much bigger and better machine called the Superconducting Super Collider. The Large Hadron Collider has been operating at 7 on 7. At 3.5 on 3.5. 7 TeV in the center of mass, and then they upped it to 4 on 4, so 8 TeV. It's designed ultimately to operate at 7 on 7, so 14 TeV in the center of mass. Tera electron volts. 14,000 GeV. Okay? The US machine was designed to operate at 20 on 20, 40 TeV. It was in every way a bigger, better machine. And it would only have cost about $12 billion. It was running over, the original estimate was $8 billion. And one of the reasons it was canceled was that it was running over, and at the end of the first Bush administration, the country was in sort of a recession with a big deficit. And then the person who actually led the fight against the superconducting super collider, to eliminate it from the budget, at the beginning of the Clinton administration, was the senior senator from Arkansas, Dale Bumpers. There was never much love lost between Arkansas and Texas, I understand. But anyway, the result is that the U.S. killed it. And that was pretty much the end of accelerator physics in the United States. I mean, we continued to fund the Fermi accelerator, Fermi Lab, but now there's no big accelerator in the United States. The one big high energy machine in the world is the Large Hadron Collider at CERN. And if we're lucky, in 2 years it'll turn back on, and maybe we'll start to see something interesting. Of course, it's already made one major discovery, the Higgs boson, which was just the completion of the standard model of particle physics. So it would have been a sensation if they hadn't found the Higgs boson. Now that they have, it's boring. And it really is the Higgs, it's not just a Higgs-like particle. But what we're hoping is that we're going to see something new, supersymmetry maybe. Maybe the lightest superparticle particle in dark matter. Or maybe something completely unexpected. But something new! And we don't know. We're going to have to wait and see. And it's entirely possible that the energy that's required to get into supersymmetry is higher than the Large Hadron Collider can be able to get to. And then the question is, will we ever get to find out if there's a supersymmetric world out there? Because it doesn't look like there's going to be any governments willing to spend the money to build a bigger machine. That may be too pessimistic, but it's another one of the things that, it's one of those nightmares that physicists worry about. Incidentally, there were 3 major colliders that were built with just not quite enough energy to make the next major discovery. So there's a big history of this happening. It's not a worry that is groundless, that isn't based on examples. Well, everybody's been incredibly patient. Thank you for letting me go so far over and asking all these great questions. I think it's time for lunch.